Looks like we can get started. It's already 11 p.m. in Beijing and 11 a.m. in US East Coast time. So my name is Xiang. I'm the host of this reading group, and this is our eighth meeting. And today we will in last meeting we talked about a little bit more about the large language model, how we can compress the model, and potentially how it could motivate future research topics in system and networking side. But this time we will switch our focus back to more traditional networking topics, which is traffic engineering. It's a very well understood and but still drawn lots of interests in the networking community. So today we will read together about a paper published last year in Sydney. It's called RedTE, Mitigating Subsecond Traffic Bursts with Real-Time and Distributed Traffic Engineering. And the presenter of this paper is Mengrui Zhang, a PhD student from Xiamen University. And also our guests of honor are Kaihui and Fei, both working with Stanley at Qinghua University. And I believe Kaihui already graduated and is now a researcher at the Zhongguancun lab. So I see our SIGCOMM board chair, Matt, is also online. So I don't know if he figured out his audio, but if you figure it out, would you like to say a few words, Matt? Not yet, so that's okay. That's okay. I think so. Our usual for first timer of our meeting typically consists of 30 minutes presentation from a student volunteer, and followed by about a 30-minute discussion with the authors to clarify the questions and the potential future research along this line of research. So with this brief introduction, I think Maura, you can start with our first agenda item, your presentation, please.
Okay, can everybody hear me?
Yes, we can.
Oh, okay. Hello everyone. I'm Mengrui Zhang, a first-year PhD student from Xiamen University, and today I'll share RedTE, a real-time and distributed traffic engineering solution for mitigating sub-second traffic bursts. And this research is conducted in collaboration with Qinghua University, Zhongguancun lab, and others. As we know, internet traffic exists bursty characteristics, leading to queue buildup and packet loss, which in turn cause network latency jitter. And this negatively impacts the user system, particularly for latency-sensitive applications like the VR or online games. And to reduce the occurrence of bursts, ISPs typically over-provision the bandwidth of their wide area network, which doubles network capacity when the average link utilization exceeds 50%. However, this method is coarse-grained and not cost-effective. So mitigating the effects of traffic bursts is in a cost-efficient manner is crucial for this. To address this paper analyzes the nature of traffic bursts. The sending rate of a flow can increase sharply due to factors such as application behavior and batch operations in network stuff. When multiple burst traffic flows compete for the same path or a link due to load imbalance, severe congestion occurs. And these bursts unpredictable and typically last only a few milliseconds, making mitigation particularly challenging. There are two traditional approaches to handling traffic bursts. The first approach is unhost mechanism, such as flow control or traffic shaping, which smooths out sending rates in unhost application or transport layer. However, these methods are impractical for ISP deployment. And the second approach employs local traffic management at network devices to distribute traffic across multiple paths. But these methods lack a global perspective and often result in suboptimal performance. So how to find a burst mitigation solution that both ISPs operate within the network while maintaining global perspective is a critical question. The traffic engineering is well suited for this purpose as it utilizes network-wide information to optimize performance and is more friendly for ISP deployments. However, traffic engineering has previously been ignored due to its slow decision-making process. Traditional traffic engineering operates on a time scale much lower than the traffic burst, as its control loop consists of three time-consuming steps. The first step is data collection. A centralized collector gathers network information such as topology and traffic demands, which can take several seconds. And the second step is computation. The controller determines routing configurations to minimize maximum link utilization, requiring seconds to minutes. And the third step is deployment. The controller sends routing updates to network devices, which then update their forwarding tables, also taking several seconds. To examine the impact of control loop latency on traffic engineering performance, this paper conducts the experiment using a linear programming-based traffic engineering method, simulated different control loop latencies and evaluates the system using packet traces from WIDE, major backbone network from Japan. As the figure shows, the link utilization increased with the increase of the offline LP computation. So the results indicates that reducing control loop latency from 25 seconds to 50 milliseconds improves traffic engineering performance by 47.8% in terms of the queue length and the queue delay. Additionally, events where link utilization exceeds capacity were reduced by 38.3%. So shorter control loop latency leads to better performance in mitigating burst-induced congestion. As shown in the figure, when the control loop latency is longer than the burst duration, congestion remains severe. However, as the control loop latency decreases, especially when it approaches or becomes smaller than the burst duration, the mitigation effective improves significantly. So to effectively mitigate burst-induced congestion, it must be close to or even smaller than the burst duration. This raises a critical question: how to reduce the control loop latency to the burst time scale. Existing traffic engineering approaches attempt to reduce latency but remain insufficient. Centralized traffic engineering methods use linear programming to calculate the optimal decision, but they come with limitations. First, there is a trade-off between decision-making speed and solution quality, which means achieving better performance requires longer computation time. And second, existing approaches ignore the latency of data collection and the decision deployment, only focusing on accelerating the computation, like POP and the NC flow accelerate the linear programming computation by sub-problem decomposition and parallelly solving. And machine learning-based traffic engineering systems leverage machine learning techniques such as reinforcement learning to accelerate computation. However, they still suffer from long delays in data collection and decision deployment, limiting their effectiveness in real-time scenarios. These systems are typically modeled as cooperative multi-agent systems, but some agents act independently rather than cooperatively, causing learning instability issues to arise, like state, which uses a straightforward combination of global reward and local reward, and but two of these goals may conflict. While solutions like DOT and Q aim to improve traffic engineering decision making using deep learning, they primarily focus on computational speeding up while ignoring delays in data collection and decision deployment. And the distributed traffic engineering methods, which rely on local information, achieve faster data collection and deployment, require multiple adjustment steps, leading to convergence times of several seconds. And none of these approaches achieve millisecond level response time. So the goal of this paper is to reduce controller latency to the burst time scale while maintaining performance comparable to centralized traffic engineer systems. To achieve this paper proposed the RedTE distributed traffic engineering architecture, making decisions based on local information and using multi-agent reinforcement learning, in which agents as network nodes are traded offline using global information. And this enables them to make globally informed decisions in real time using only local data, avoiding slow multi-step conversion. And RedTE consists of centralized controller and distributed network agents. On a large time scale, agents report traffic demands to the controller and periodically download updated models. And the agents are deployed at the network edges, simplifying decision making. And during each controller, RedTE routers measure traffic demands, local utilization, and local bandwidth. Then each agent uses the information to infer the split ratio of redefined paths, and finally update forwarding tables accordingly. And to achieve both speed and performance, this paper addressed three key challenges: ensuring collaboration among all agents towards global optimum, and ensuring faster convergence of agent training, and reducing decision deployment. So for the first challenge, ensuring collaboration among agents, Since agents operate with only local information, it is difficult to achieve the best overall outcome. Instead of each agent acting greatly based on its limited perspective, we need a cooperative multi-agent system where routers communicate and align their strategies. So the key question is, how can these agents coordinate effectively to contribute to the global objective rather than just optimizing their individual performance? To address this challenge, this paper models the traffic engineering system as a cooperative multi-agent system, leveraging the MADDPG algorithm to enhance collaboration. And by introducing a global critic model, MADDPG aggregates the policies of all agents and assess each agent's contribution to overall network performance. This tracker feedback mechanism allows agents to learn and adapt their strategies, ensuring more effective operation and optimization of the global objective. Through precise and separate feedback, agents can align their decisions to improve network efficiency rather than acting greatly with limited local information. And this figure shows the training with MADDPG algorithm in RedTE control. And for the second challenge, ensuring fast convergence of agent training, we must address the complexity of traffic-driven environments. In real networks, traffic arrives dynamically, making state transitions and rewards unpredictable. Due to this randomness, even a well-chosen active may yield a low reward if sudden high-low traffic matrix arrives, slowing down the entire training process. And this variability extends convergence time, making it critical to design robust mechanisms that stabilize training performance. The traditional training methods sequentially replace training traffic metrics, introducing random starts slow convergence. And to address this paper adopts circular traffic replay with shorter traffic matrix. Subsequent repeatedly processed multiple times within each training epoch before moving to the next sequence. And this approach helps reinforcement learning models recognize traffic evaluation patterns more efficiently, accelerating convergence. As shown in this figure, the normalized maximum link utilization performance of RedTE is approaching the optimal gradually, which means the quality of the agent policy is getting better and can be trained through conversion. The third challenge focuses on reducing decision deployment time. Now, updating large forwarding tables is a major bottleneck, contributing to 60% of total control low latency, while reducing the number of table entries could speed up updates, but it would come at the cost of degraded traffic engineering performance. So to address this challenge, this paper introduced deployment aware reward function that optimize update policies to achieve effective traffic engineering will minimize unnecessary modifications to forwarding table. The key insight is that multiple update policies can yield similar traffic splitting effects, but require different numbers of table modifications, which directly impact the deployment time. So the reward function incorporates both traffic engineering performance by minimize maximum link utilization and update efficiency by minimizing table modifications, ensuring that unnecessary adjustments are avoided. So RedTE is implemented using the baffled Tofino platform and deployed in a real-world test and evaluated in both testbed and large-scale simulations. RedTE reduces maximum link utilization by up to 30% and maximum queue lengths by 54% in the Wang test. And RedTE reduces maximum link utilization by to 42% and maximum queue length by 75% in the simulations. And it achieves control loop latency of under 100 milliseconds, and it's 200 to 300 times speed improvement over traditional traffic engineering system. So in conclusion, RedTE shows that traffic engineering can effectively mitigate traffic bursts if its control loop latency is reduced to the burst time scale. And this paper addresses multi-agent reinforcement learning challenges in distributed traffic engineering scenario with 3 key innovations. The first one is cooperative multi-agent training. The second one is circular traffic replay. And the third one is deployment aware reward function. And the experimental results show that RedTE's superiority over existing traffic engineering methods. And that's all.
Okay, yeah, Maury, thanks for the presentation. I think, yeah, I know we are short on time, but I do want to give some high-level comments in terms of your presentation, not on the paper, but just the presentation. I think you did a really good job trying to lay out the background of the paper. But when you talk about the details, I think there are, like I said, there are 3 key design points, right, in your presentation. I think one is to model, to leverage cooperative game theory to essentially to have multiple agents collaborate to make distributed traffic engine decisions that towards a common objective. That's your first design point, right? And the second one, the second one is yeah, I forgot the second one. The second one is train with traffic matrix replay, but instead of but you use circular traffic matrix replay, right? That's what you did. What this paper does. And the third one essentially is trying to incorporate routing decisions as part of the reward function, right? So this way, routing changes as part of the reward function, so that we can try to make a so-called deployment aware decisions, right? So that's what that's the third design, the deployment aware reward function, right? So, but usually when you try to understand the paper and when you try to read the paper, can you go for each one of them? Can you go into a little bit details? Because I think you are just, the high-level idea is really easy to understand. But what's the details? For example, in this deployment award reward function, how do you basically how to design different items in this reward function? What's the rationale behind designing this using reward function in this form? Any intuition, or if it's okay if you don't understand, because we do have authors here where I can just ask the authors the questions, right? But this is supposed to be a presentation. It's okay to use the conference slides, but you know, in order to make the presentation, improve your own presentation skill, you need to go into, you need to educate the audience, right? Instead of just telling them the high level points. This is only telling the high level points is not a good presentation for paper study. It's good enough for a conference presentation, but it's not enough for paper study.
Yes, I only add some background in these slides, but ignore the details of this paper.
If you so let me ask another question. Do you understand the details? For example, what I just said, deployment award reward function. Why you used you minus alpha times maximal blah blah, the summation of FDIJ. Why that is a good reward function? Or why the paper propose this a linear form of this reward function? Why can I just use the item marked in the red box? Why can't I just use this to time with the utility, the first Umax? Can I do that, or or that's not a good idea?
The first one is to describe the network congestion level, which use the maximum link utilization. If the MLU higher, means that the network is more congested. And the last this part is try to reduce or avoid the unnecessary path adjustments to make sure that, as I said in this slide, to make sure that it can reduce the decision deployment time. So they add this part of functions in the reward function.
Yeah, but why they add these two together? Why can't we use multiplication to make the item in the red box as a coefficient of the utility function? Would that work or not?
I think there is no necessary to multiply, because
I know, of course, it's not necessary, but I mean, can we do that? Why we use a linear combination of these two items instead of a multiplication item relation between these items? That's my question, right? You understand the question, right?
Yeah.
Okay.
Yeah, in my opinion, maybe because if we use the multiplication, it may cause this part too strong and reduce the performance of this part. But it's only in my opinion.
Then what if I use I take a log of the right item and then multiply with it with the Umax? I know I'm picking a bone here, but I just want to use this example to basically when everyone is reads the paper in details, and especially when anyone is making the presentation, you need to think deeper about the design decision taken in this paper. And only in that way you can try to basically, suppose you are now a lecturer talking about this paper, right? So that's how you teach people, how you let your audience understand about this, right? Instead of just reading the points. You understand, right? Okay. Yeah, I'm just giving, this is just a suggestion, but I guess now we can switch, naturally switch the question back to Fei and Kaihui. So can we start with this question? So why use a linear combination of these two instead of maybe a multiplication or log and so on? And any considering, or did you guys just try different ones? Think this linear one works the best, so that's how you make the decision.
Yeah. Hi, Chao. I'm Kaihui.
Hi, Kaihui. Yeah.
This is a very good question. But I forgot the details why we chose a linear function. But I think we have done many experiments about this function to balance the object of the utilization and the number of updated entries. So as a result, we want to get the result of to reduce the utilization and to reduce the number of updated entries. So I think you can say the alpha is a parameter. I think we can give this we can give the parameter the choice of the parameter to give the user. So you think
this meeting is being recorded.
In some networks, many there are users may care about the utilization more or care about the update time, update latency. So so I think we can try other functions. Okay, that's okay. But this basic idea is we should consider both of the utilization and the number of updated entries. So okay, this is my.
So I see.
Yeah.
Good. Okay, great. I think a linear combination intuitively makes sense because it's the most simple form, right? So I think that makes sense. I'm just using, but as you said, maybe just maybe there may be other more complex form or a way to combine these two items to make even better reward function, right? That's possible. But then if we accept that, okay, now it's okay to use a linear one because it's simple, it's easy to understand. Then in the right item here, for example, you have this FDIJ, right? So I think in rough sense, it means the number of updated flow rule entries, right? If you make a certain decision, right? So how do you calculate the number of updated entries? I guess my question would, so you remember back in 2013, 2014, there's this paper called Z Update, right, from Harry, and also Diagnosis from Jinxin, right, talking about the SDN update problem, how to compute the update plan, right? They're like this, like over 10 years ago. But in those papers, I think they have this so-called disruption-free and also minimal number of updated entries. So essentially, it's a quite a way to calculate the number of route entry updates needed to finish update intent or a network-wide update intent, right? So because so when we talk about updating an entry, there are different options. You can insert a new entry, you can delete, you can also update, and also update sometimes can be decomposed into a delete and insert. So right. So I know this might maybe just a very minor implementation detail, but what how in your prototype, how do you calculate the number of updated entries needed here? Am I making any sense here? Sorry.
I understand your question. That's a
Yeah.
very great question. I think firstly we have a raw table with a fixed size, so we can check if one entry has different results from the IO actions, right? Yeah. So we can give these results in order, so we can check which entries has changed this time, so we can compute this number of updated entries. That means if we could keep more entries to be non-changed, it is a very good action from the IO agent. Okay.
I see.
Can Fei, do you have more answers for this question?
Yeah. So the problem is that how we can calculate the number of updated entries. First, the so the we in our the root table, the number of updated entries is is grow linear, yeah, with the difference between the t splitration between the two consecutive time period. Yeah, that is to say the difference the period difference between the two the of traffic splitration between two consecutive time period. The bigger the more number of update entries. Yeah, that's a linear correlation between them. Yeah. So let's give an example. In first time period, and A toward and E has three paths: ACE, ABDE, and ABDCE. Yeah, and the traffic splitration is one is 20%, and 18%. In the second time period become 10%, 13%, and 16%. Sorry, 16%. Yeah, that means the two and the first two paths traffic splitration changed, and yeah, it's only changed 10%. Yeah, so in our in under isolated that we use 100 100 terms to express the traffic split the region. So the number of updating entry is 100 multiplied by the 10%. Yeah, that's result into 10 entries to be updated. So yeah, that's my
Yeah,
that's my answer.
his point. I think in summary, we can use split ratio from IO agent to compute the number of updated entries. That is the different how many different entries we should to make. So
I
this
see.
is
I see. Mhm.
we have the total number of entries we have. Yeah.
I see. So this total number of updated entries is network wide. It's not for just one router. It's network wide, right?
Yeah.
Okay, got you. Yeah.
Yeah,
So sorry, you were saying?
yeah, that's a max. Yeah, that's a max operation. Yeah, the
Okay.
max is on the all routers on the internet network.
I see. I see.
Yeah.
So yeah, I know I have been asking a lot of questions, but if any audience has any question, you can either just speak up or if you feel a little bit shy, just type your question in the chat. I will keep monitor them. So, but following regarding this training and how you deploy the first design, actually, I think I definitely understand design number 3 and number 2, but I'm even though this is the second time I hear the presentation, the first time is when you guys did it in during Sydney, but still for the first design, I'm still a little bit fuzzy how we enable cooperation or collaboration between different routing agents. So because my question is also related to, for example, what's the decision each agent needs to make? Do we have to? I think I probably even asked this question before, but what would is there like a routing decision involved? And if so, how do you guarantee a consistency? For example, suppose there's one agent at at router 1, and there's another agent at router 2, and there's another agent at router 3. Essentially, one agent for each router. So if router 1 decide to forward to router 2, router 2 decide to forward to router 3, and router 3 makes a decision somehow decide to forward to router 1, then you form a routing loop, right? So how do you avoid them? Or if it's a probabilistic thing, how often do you observe that in your experiment? Or
A
route
very
or
quick, yeah,
Mhm.
sure.
Yeah, so
A very quick answer. Yeah.
yeah, okay, go ahead, please.
Yeah. For to avoid the routing loop, uh we have some fixed forwarding paths. So the our agent is then to trace some forwarding paths. So this path will give the guarantee there are no routing loop. Yeah. So we have some we have K forwarding paths in advance.
Yeah, those paths are end-to-end, which are pre-configured. Yeah, that can implement
Okay,
it by
I see. So
SVR, MPLS or SRv6. Yeah.
So okay, so the reason I'm asking is you guys probably already read the DSD decentralized SDN paper from Google and Berkeley, right? It's also presented at SIGCOMM last year. I think it's the first author is Alex,
The one?
Decentralized SDN. I think it's in the final day of SIGCOMM 24. Decentralized SDN is a Google and Berkeley paper. So they essentially what they did is they offload the computation of routing into they offload the computation of routing and traffic engineering also onto router. But to maintain consistency, they essentially use source routing. They use source routing. Did you guys do similar things, or you guys handle this consistency differently?
Yeah.
Because
source routing.
Source routing. So it's, I think it's similar in essence. Maybe there will be difference in details, right? But in essence, it's similar, right?
Yeah.
Okay, got you. And then how do you so sorry, I know Bo has typed a question in the chat, but before I read it, I have one more follow-up question on this. So how do you handle like a topology change or routing changes? So for example, topology change, you can have link down, you can link up, you can also add new routers, right? That's topology change. And by routing change, I mean you mentioned that we may pre-configured a set of forwarding passes, and we ask agent just to pick among them, right? What if I update this set of pre-configured paths to add some new ones or to delete some old ones? In either cases, do you have to retrain your model? Because you do have a offline training process, right? Do you need to retrain that when topology or routing changes, or you don't have to do that?
Yeah. So to handle the topology change, we can, yeah, we have the limitation. We just can handle the scenario, the several link field. Yeah, but we cannot handle the router node is added. Yeah, new router or new link is added. Yeah, this scenario is cannot handle it.
I see.
Yeah, so if we in the former scenario, yeah, when the link is down, yeah, the path we said the path congestion is very congestion. Yeah, that means the link utilization is set much exceeding 100%. Yeah. So let the model to automatically to adjust their traffic splittation to handle this.
I see. Yes, I think that's a very clever way to do that. Yeah, I see. Cool. Okay. Now I need to read Bo Ran's question. So Bo says, I'm very glad to have the opportunity to communicate with you. And he already read your article before and even looked at your open source code. But he did make a comment that the open source code seems to a little bit like lack management or doesn't even match the content of the article. So to basically sense your open source artifact, right? So do you still maintain that or update that? And he's wondering if your state transitions are in line with the normal reinforcement learning process.
Yeah, we just open source some of the code because the whole project is cooperated with some organization. Yeah, this organization has a privacy to yeah to open source privacy in con, con,
Okay, so
consideration.
essentially,
Yeah,
I
yeah,
see. So basically, there are some certain NDA in place, preventing you releasing the complete prototype, right?
yeah, yeah.
Okay. Okay. Then Bob is wondering if your in RedTE in your learning part, if your state transition are in line with the normal or just typical reinforcement learning process, or is there any special design over there? The state transition. If I didn't pronounce it correctly, you can refer to the chat of Zoom to see the question yourself.
Let me understand this question. Yeah, the question is how to handle the traffic pattern change.
No, I'm not sure that that's I understand differently. I understand is that because you use reinforcement learning, right? And
Yeah,
you define lots of different state, and you need to transit from between between one state to the other. And then
yeah.
this state transition, is this just a typical way in your modeling or in your training part? Is this just typical as normal reinforcement learning process, or is there any unique challenge you need to uh, handle in the setting of using reinforcement learning for traffic engineering?
Oh, yeah. The challenge lies in the last design. Yeah, uh uh we uh we face the challenge the challenge we faced is sorry the second design. Uh
Mhm.
the challenge is laying the uh yeah the traffic engineering is a very dynamic scenario. In the scenario, traffic is continuously injected into the network. Yeah, we can call traffic driven environment, which is not same as the standard environment uh the reinforcement learning can handle. Yeah, that means the state transition process is not only driven by the agent action, but also the arrival of network traffic. Uh, so since the traffic arrives randomly, the reward is also random. That means a good action may receive a very bad reward because uh, maybe a new traffic matrix sequence with a very high load or wrapped. So the training the training in the traffic engineering scenario can takes a very long time to converge. Uh, uh, we handle this is to to mitigate to mitigate the traffic dynamic in the training process. Uh, we propose our the circular traffic matrix replay technology to address this challenge. Yeah.
I see. So, Paul, does that? Oh, okay. Paul has a follow-up question. Are there any connections between each of your states? How does your action influence the next state? Because I noticed that your previous action is used to calculate the next incoming traffic matrix. Shouldn't a traffic matrix come in first and then an action be made? So Bo has this follow-up questions.
Okay, okay. Just so we let me understand this question.
Yeah, I understand this point. I think there are two major scenarios in reinforcement learning. I think one is I think it's closed mode reinforcement learning. The another one is we call input driven scenario. So for the in contact for the context of networking, I think this environment is input driven because we usually have new traffic into the network. So this state is this state transitions is not only not only by the action of our agents, but also this transition is because the input traffic. So because we have replayed the traffic metrics, so this our agents will then to handle this traffic. So they will meet some similar scenarios and learn this traffic pattern, so they can learn to make good action. Okay, so I think if you are interested in this reinforcement learning environment, I think you can study more we call import-driven reinforcement learning. Okay.
Okay, thanks, Kaihui. We also have a question from Adrian. He said, is there a central system that collects information and interact with all the agents? Or how exactly does the global critique model work?
I think in the deployment phase, we don't have a central system. Yeah. In the real world, we like these agents to distributed work together. Okay. How does this is a very question. The global critic model only work in offline. It only work in training phase. Okay. In the deployment phase, we don't have the global critical model. We just have some our agent in these routers. They input this traffic and some information. Then they take actions. Okay.
Okay, cool. We are running out of time, but I do want to ask a question that I typically ask every authors joined in previous meeting. So, what do you envision the next step for RedTE? Or in other words, distributed traffic engineering? Is there any major? What do you think would be the next major problem you want to address, or you think someone should try to solve? This goes to both Fei and Kaihui.
Okay. you see, you can see there are many limitations about RedTE. I think in the future we can make some optimizations in for the failure tolerance and make some more flexible routing decisions. Yeah.
Yeah, I see. But I think that could be very challenging because routing consistency is basically the more flexibility you give it to routing decisions, the more likely you have the more likely you could end up in certain you have to deal with routing loops and or inconsistency and stuff and other stuff. So there's a trade-off between like flexibility and stability or flexibility versus efficiency. That's just my 2 cents. It doesn't have to be right.
You can train some
Mhm.
agents, some formal agents. Yeah.
Mhm.
If they are output some illegal actions, you can give them some bad reward. I think yeah, combining reinforcement learning and formal verification is a very good direction.
Indeed, yes, it is. I fully agree. Yes. Okay, that gives formal verification a new place to work. Okay, cool. So we're already 2 minutes over our 1 hour meeting. I know people probably have more questions or about more follow-up questions or clarification questions to ask Kaihui and Fei. So please, by all means, you can drop emails to them, and I think they are also in Slack channel as well. So try to find them and ask your questions. And but since we are running out of time here, so we will end here today. But I hope to see many of you next week. Well, I think next week we probably will. I'm still contacting different authors to see which author will be available, but possibly it will either be a Merriman paper or a programmable hardware paper from SIGCOMM in the past couple years. So, okay. So I think we can call it a day. So for everyone, have a good day and good night. And also thanks Mengrui, Kaihui, and Fei again for staying up late and joining us and leading our meeting. Thank you so much.
Okay, thanks, Chao. Thanks everyone.
Yeah, thanks everyone. Bye.
Bye.